My name is Hao, and I work for the Apache MXNet Science team at Amazon AI, which is part of AWS. And today, we're going to introduce a new package that will help you with accelerating your NumPy workloads. So firstly, let me introduce a bit about Apache MixNet. So it is an open source deep learning framework. We have a team dedicated on it at AWS. And this MP on MixNet is our new NumPy compatible interface that will allow our users to retain their familiar NumPy interfaces, functions, APIs, meanwhile also leveraging the parallelism of modern computer hardware. And we also want to provide extra deep learning related features to our users. So let's visit what does this exactly bring. So one thing we want to ensure is definitely the interoperability with NumPy. Another thing we bring is the parallel acceleration for all the existing NumPy operators. And also we are adding extra operators and functions for deep learning related workloads. And one last thing we want to add is the automatic differentiation functionality. So let's dive deep into each of them. So let's take a look at this piece of code. We are importing the NumPy module from MixNet, and we also imported the official NumPy as OMP. And we are initializing two tensors within, we're initializing two MXNet NumPy ND arrays, and we are trying to add them up with the official NumPy's function. We can see this works, and the result is still a MXNet NumPy ND array. And we can also sum on a certain axis of the result. The result is still a MXNet NumPy ND array. So we can see this is interoperable with official NumPy. So the next thing is that we are bringing parallel acceleration to the operators. So here, let's take a look at this example here. So we're importing the official NumPy just as MP, and we're initializing two large tensors, which one is 2048 by 1024, and another is 1024 by 4096. So we initialize two random tensors as left-hand side and right-hand side, and we're trying to perform a dot product between them. So we tested on a really beefy server on AWS EC2, and this server has 32 CPU cores, which is already quite beefy, very, very powerful. So the dot actually took 0.08 seconds. I wouldn't say this is slow, but you would expect something more from when you are paying for that kind of powerful server, right? So let's take a look at when we switch the library to the MP on MixNet. So here you can just, here we're just switching the library, but we're keeping the code the same, right? So one thing to note is that right now we are just setting the default type to be in MP on MixNet is just a single precision float. So we don't have the extra typecast here. And this dot now on the same machine finish within about 0.06 seconds, which is a 1.3 speed up with just a drop-in switch. So we want to take it further, and we want to put this operation on GPU to further speed it up. So now let's see how do we put it on GPU. So here we have a call called asInContext, which will just put your tensor on GPU. So the GPU if you have multiple GPUs, you can just index them by their ID. So here we're just using one GPU, and the ID is just 0. So we just put all those two tensors onto the 0th GPU of our system. And if we just still perform the dot product as usual, the computation will just automatically happen on GPU. So this dot product finished within 0.002 seconds, which shows about a 42 times speed up with just 2 line changes. So the third feature I'm trying to talk about is the new extra operators that we're adding in the NPX namespace. So which include a lot of deep learning specific functions like convolution operator, pooling operator. So like let's take a look at what is convolution operator. So you apply a kernel onto an image, and then you multiply the weights in the kernel or filter, somebody may call it, element-wise with the input data that it covers, and you sum them up to get the final result. So pooling is a bit similar, but without the filter, you just try to derive one number from a certain pool. So convolution is used widely as a feature extractor on images. So let's take a look at this example. Those are the filters or convolution kernels trained on the MNIST dataset, which is the handwritten digits. And we can see that it's trying to figure out, it's trying to find out the dots and also features like dots and edges and some patterns. So this convolution really works well on a lot of data, even on audio data, image data, video data, as a strong feature extractor. So for the activation functions, we're providing a wide range of them, like sigmoid and also leaky ReLU function. So all those are easily implemented with official NumPy, but we're just making your life easier by providing them directly to you in the NPX namespace. And we also provide batch norm, dropout, and so on. So the last feature I want to talk about is the automatic differentiation. So when you are building some model and you need to know your output's gradient with respect to its input variables or the parameters of the model, if you just want to write it in NumPy, because NumPy does not naturally provide the backward function for you, you'll have to implement it yourself. But here with the automatic differentiation, we are doing this for you, and you can get access to your backward gradients in an easier way. So let's take a look at this code example. So we are importing an extra module which is called AutoGrad. And here we are just performing another dot product between the two tensors. Okay, thank you. So here we're just performing another dot product between the two tensors. And before we perform this, we want to attach two extra buffers to the two input tensors to hold their gradient when the backward propagation is done, right? And then we wrap the computation up with this autograd.record scope, which will keep track of what kind of operations you have gone through. And when you want to compute the gradient, it can just backtrace it for you and do the backward computation for you. So now we're just performing this dot product within this scope, and the system have record of it. So after this, when you want to compute, okay, what is the gradient on my left-hand side and right-hand side tensor, you just call backward on the out. So now, after this call, the gradient for both left-hand side and right-hand side will be in their dot grad buffer respectively. Okay, so with all those being said, let's now take a look at an example on how do we build a model with this new interface. So let's do it step by step. So first, we definitely want to get our environment ready. So we are importing our NPX module. So this is an extra step that we are doing because historically, MXNet was not supporting a lot of the features, and we want to maintain backward compatibility for the legacy users. So we added this extra call to switch MXNet to its NumPy compatible mode. And since we are also using the AutoGrad functionality, we are also importing the AutoGrad, and we are borrowing the data loaders from Gluon interface. So we're just importing all those four things. So now we want to prepare our data loader. So we're operating on fashion MNIST data set, which its examples looks like this. It consists of images of size 28 by 28, and they are all pictures of the fashion goods. So we want to classify them into their corresponding categories. So that is our task. So for the data loader, we're just borrowing the Gluon's vision data set, and we are designing some pre-processing to it. And then in the end, we get 2 iterators for the data set, for both training and test data sets. So we will be trying to make this more NumPy native or friendly. And so note that we are also leveraging parallelism here. We are specifying the number of workers, which will be the workers, the number of parallel workers used for the pre-processing of the data. And now let's move on to actually build our model. So we've got the data source ready. And the design of the model is actually really simple for easier understanding. And so the model is designed to be a 2-layer, multi-layer perceptron with so the input size is 784, which is the result of 28 by 28. So it's 784 pixels. And we have a hidden layer of size 256. And we are categorizing all the inputs into one of the 10 categories. So the number of output is just 10, right? And here we're just initializing, we're randomly initializing all the weights and bias for the 2 layers. And we're collecting them so that it's easily managed into a list we call params. For each of them, as I've shown previously, we're attaching a gradient buffer to it because all those would affect the output of our model, right? So they are all the variables of the model's output. So we want to update them, and so we want to hold the gradient. We want to compute and hold the gradient of them. So now let's define our model. So let's take a look at this line first. So we are reshaping the inputs. So those were batch size by 28 by 28 pictures. We want to reshape them into batch size by 784 pixels, right? And so so for the inputs, after they are reshaped, we dot product them with the weight, and we add the bias of the first layer to them. And then we pass the output of this into the activation function, which is a regularized linear unit. So regularized linear unit is a kind of activation function, which is defined as if your input is bigger than 0, then we just return that input. But if it's less than 0, we just return 0. So it's you can see it's easily implemented with native NumPy. But we are also providing you this in the NPX interface, in the NPX namespace, as I just said. And so after the activation function, we get the output of the hidden layer, right? We further dot product with the second layer's weight, and we add the bias of the second layer to it, correct? And then now we reach the output for our model, right? So this is just the forward function of the model. We will not be handwriting our backward function because we are just gonna use the automatic differentiation to handle it, right? So now let's also define, okay, how do we measure how our model is performing, right? So we want to define a loss function. So now we're using the softmax cross entropy loss function. So softmax is a function that will, so for any output, it will just compute the probability of each output. So the output of softmax will just sum to 1 for any single input sample. And so for the loss, we are computing softmax, so which will return the probability for each of the 10 categories of every single sample from the data set. And we are taking the log of that probability, and we are multiplying with the value of that label. So if the label is 0, then we're just multiplying with nothing, right? So if the label is 1, which means, okay, it's that category, then we are just multiplying it with 1. So we sum all the loss up, then we get the total loss of this batch. And so this is the loss function, and this is softmax function. So we also have this available under NPX namespace. And now we define the optimizer, which is a stochastic gradient descent. So for each parameter in it, we take its gradient after it's computed, and we multiply it with the learning rate, and we average it by the size of the batch. And we, so here we are also adding a regularization trick, which is a weight decay, to regularize the model to prevent from overfitting. So after that, we also want to evaluate, say, because loss is just a floating number, right? We also want to, it's not direct. We also want to see, okay, how accurate is our model? So we are also defining those helper functions to measure the accuracy. So here we have, so the input is actually a batch size by 10, right? So we are trying to get, okay, among which of the 10 values do we have the maximum value? That is, we want to use that as our prediction of the model. So we're doing argmax here, and we're comparing against the label. The label is just a single number from 0 to 9, which denotes which class it is, right? So if it is the same, then we say we have a correct prediction, right? And for evaluating the total accuracy, we want to go through every sample in the data set, and then we want to calculate the number of correct examples using this function, and we are also summing up the number of the total number of examples. So dividing those two, we get the rate, the percentage that we're getting it right. So with all those set up, now let's get ready to train our model. So we just train for a very short, very small number of epochs. And so here we can see that for each epoch, we are going through the training data set, right? And we are doing the forward pass here wrapped in the record scope so that the system will handle the tracing of the operators for us. And then since we want to minimize our loss, so we are computing the gradient of all the parameters with respect to the loss, right? So now we call the loss backward function. So after this call, all the gradient for the parameters we defined previously will be ready in their .grad buffer. And then we can just call the updater, the optimizer, to optimize those parameters toward our ideal result. And so we are also keeping track of how our model is performing during the training. So we want to compute the loss, we want to compute the accuracy. And so at the end of each epoch, that is, we finished one round of training, we also want to validate it on the test data set to see how it is actually doing in the wild, right? So at the end of each epoch, I'm printing out the epoch ID and the loss, the accuracy on both training and test data set. And here's the visualization of a sample training. We can see that with just that code, our loss is constantly decreasing, and there's no big gap between the training and test accuracies, which means we are in pretty good shape for this model. You can actually build more complicated models too, but just with the similar tricks. And definitely you are just not training a model for fun, right? So you want to put it into production. So we are providing an easier path for you. So other than Python, we support 7 other languages, which includes Julia, Clojure, R, C++, Perl, Java, and Scala. So any production system your engineers work on, we can try to make it work on it. So there are separate tutorials on how to export your model and deploy it on different language bindings or, yeah. So another thing I want to cover is that we do have an ecosystem. The first thing in the ecosystem is that we have developed a deep learning textbook, which is totally based on this new interface, actually. So it comes with code and mathematical formulas, and also we provide a discussion forum together with it. So its Chinese version has already been published, and it was a #1 bestseller on the biggest online retailer in China. So it's also adopted by more than 25 universities globally as their textbook or reference book for their deep learning courses. And it's accessible for free at this link. Very, very short. And another part of our ecosystem that we are providing a lot of ready-to-use toolkits. We have Gluon CV for computer vision features. We have NLP for natural language processing. We also have a Gluon TS for time series modeling. And graph neural networks has been hot these days. We are also having a library called DGL, Deep Graph Library, on graph neural networks. So what do we want to do in the future for this new package? One thing is definitely we want to extend our coverage to more functionality features, operator APIs in official NumPy. And we also want to push our performance to the next level continuously. And one way to do it is that we are integrating with Apache TVM, which is a deep learning compiler for generating tunable computation kernels on different devices, actually. And we also want to enable deployment on various hardware, including the popular CPU, GPU, and also ARM-based devices, such as Raspberry Pi, and also via our cooperation with Apache TVM. So the slides are over. So all the scripts shown are available at this link. So this link is also available on this talk's schedule. I'm also gonna show the actual running of some of the code I just showed to you. Okay, so this is a part that we that is used to show the interoperability between us and the official NumPy package. So if you run this, we can see that here the type of, so after the creation, the type of A is just our NumPy ND array. And after calling the official NumPy's function, we still get an mixnet NumPy ND array. And so yeah, this pretty much shows the interoperability between us and official NumPy. So this, so we can also like verify that this result is correct by maybe we can print out the results. Say if we just insert a cell and we print C, and so if we want to do this in official NumPy, we have a way to cast our ND arrays to official NumPy ND arrays, which is the as NumPy function call. So if we run this, we can see that the results are pretty much just the same, right? Which verifies the correctness of the computation. So here is an example of the autograd functionality. So here, when we are attaching the gradient, we allocate a new buffer to it. So like if we can try to print one of them out, and we can see the result of it after the backward call. So after attaching the gradient, the buffer contains all zeros. So it's like written, right? So after the backward call, it's filled with the gradient with respective of out with respective to left-hand side. So you don't have to actually implement the backward function on your own. So here's the model training example that I just showed. So we're importing without a problem, and we are preparing the data loader, and we are initializing the parameters here, and we're defining the model computation here, which is exactly the same code, which is also available in the GitHub repo. So this is the loss part, right? We're calculating the cross entropy of the softmax output, and this is the optimizer. And this is the definition for the accuracy metrics. And here is the actual training loop. So let's run it to see if it works. So we can see after epoch 0, our accuracy is about 68%, and then the loss is decreasing. Both accuracies are kind of in a trend to go up. So we're training, so this just happens on CPU. If you put it on GPU, it could be even faster. But since this is a really small neural network, then we just don't even need a GPU. So after 10 epochs of training, we can see we are reaching a training accuracy of about 85% and test accuracy of 82%. So now let's maybe take a look at how this is doing on actual data set. So let's visualize the predictions. So the label above is the ground truth, which is a t-shirt, and now we're predicting it as a t-shirt. So we're good. And so for all the other pictures, the one above is the ground truth, and the one below is our model's prediction. So we can see we're doing pretty good on 4 of those, and for this we're kind of tricked, right? And I would say this one really looks like a shirt. Right, and yeah, so that's pretty much it. And any questions?
I'm just curious if you could go over like some of the main highlights of how MXNet is better than TensorFlow or PyTorch or like other common deep learning tools. And then my other question is, if like the original NumPy updates and stuff, are you inheriting from that, or like how does that get pulled into your code?
So to answer your first question, I think firstly we definitely have actually good support for distributed training. That's one point. And also, as I said, we have quite smooth deployment paths. We also, as I just mentioned, we have cooperation with Apache TVM on also deploying your model to your edge devices if you have any. And on the other hand, about the updates on the NumPy side, we have a team with more than 10 people dedicated to keep this package going, keeping it updated with the latest NumPy. So right now we are matching the behavior of 1.17. So if 1.18 comes out, we also identify the gaps and keep working on it. Okay, thanks for you. Thanks for your attention, and feel free to reach out to me on GitHub if you have any questions regarding this package.